Hi, my name is Alex. Today I would like to tell you about two articles I have read in this semester. These articles report various problems and practical applications of circumplanetary disks and gas giants. Scientists generally distinguish three stages in the planetary evolution of gas giants: accretion of solid material, accretion of solid material and gas, and accretion of the gas remains. The building material, before falling onto the gas giant, becomes part of the so-called circumplanetary disks. The typical forming gas giant is shown on the screen. The right-hand panel zooms in on the circumplanetary disk. The two crosses in the right panel are first and the second points of Lagrange, while the black curve represents the Roche lobe of the planet. The circumplanetary disk in the first two stages of evolution is in a state of dynamic equilibrium. For the loss of gas and solid material caused by accretion onto the gas giant, the circumplanetary disk compensates it by attracting material from the circumstellar gas cloud. At the final stage of evolution, the gas giant exhausts all the reserve of the building material, resulting in circumplanetary disks collapsing on the gas giant. For a variety of reasons, circumplanetary disks are of great scientific interest. Circumplanetary disks may play a role in capture of asteroids and continuation of planetary mass growth after initial collapse. However, evolution of circumplanetary disks is still poorly understood. One of many problems is the transfer of energy and momentum from inner parts of disk to outer parts of disk. In the first article, the mechanism of shock waves was investigated. A two-dimensional hydrodynamic simulation was carried out with the radiation losses taken into account. Equations are on screen. Unlike other previous simulations, the coordinate system took the planet itself as a reference point, which led to several advantages: exact conservation of angular momentum and reduction of rounding errors. The time dependence of the total mass of disk according to various models of circumplanetary disks was obtained. Results are on screen. All models, except for isothermal one, came to a stationary solution. The isothermal one was discarded on the basis that it did not result in a stationary solution. The spatial dependence of surface disk density, according to various models of circumplanetary disks, was also obtained. Results are on screen. Surface density of Himalaya family satellites is also on the screen. Circumplanetary disks also may have unique signatures, thus making possible detection of forming planets by detecting their circumplanetary disks. In recent years, various observatories discovered many young single-star systems with spectral characteristics of binary systems. One example of such systems is on the screen. This image of PDS-70 system is the result of synthesis of observations of 3 radio telescopes. For some reason, despite clearly being a single-star system, PDS-70 has additional light source, PDS-70c, that has luminosity comparable to one of the main star. Some scientists suggest that accretion under right conditions can have luminosity comparable to one of M-class brown dwarfs, and thus explain the paradox. In the second article, spectral distribution of energy, or SDE, was calculated for the circumplanetary disk and planets. Results are on screen. Red curve represents SDE for hot star planets. Blue represents SDE for cold star planets. Black represents SDE for circumplanetary disks, and green represents SDE of young M-class star. It was confirmed that under certain conditions, circumplanetary disks have a luminosity comparable to the one of brown dwarfs. For cold star planets, the spectral distribution of circumplanetary disks dominate the spectrum of the whole system, which allows us to neglect the planet's contribution to the whole spectrum. For hot star planets, the contribution of the planet itself to the overall spectrum is significant, and therefore it cannot be discarded. To sum up, circumplanetary disks may have answers for many mysteries of early stages of star systems evolution. It's important to continue observation. Attempts to generalize, for example, change two-dimensional simulations to three-dimensional simulations, should be continued.